Okay, thanks. Yeah, I hope this will be a short talk. We just want to share with the community some of the lessons and experience we learned from this migration process from Redshift and Spark, and some of the context why we do that. So a little bit about my company, Stitch Fix. How many people have heard of Stitch Fix on the East Coast? Oh, I'm surprising. It's an online personal clothing styling service founded by our founder Katrina Lake in 2011, and so it's happened almost 6 years. Basically, the idea is like we send a box with 5 pieces of clothes inside to a client, and they don't know what's inside the box until they open it. So if they like, they can keep it and buy it and check out. If they don't like it, they put it back and send back to us for free. So it's really, you can think of it as a recommendation service in its core. So it's very important for us to get the thing right. We only have 5 chances, basically. It's like a five lottery inside the box. And our data science team is highly organized around this recommendation engine. We want to get this right, and we want to use the feedback from the client to guide us for the inventory as well. What kind of thing we should buy, what kind of thing we shouldn't buy anymore, and to get a really high accuracy for the recommendation system. Our philosophy is like a combine a human stylist, their own judgment, plus our algorithm. Internally, we have done a lot of A/B testing. Like this combination beat human alone and beat algorithm alone. So that's basically why we're doing this. So we have a kind of big data team, and I work on the inventory data infrastructure and analysis kind of project. The biggest table, we don't always have big data actually. As an e-commerce company, we're not as big as Amazon, but we are also not like other internet company provide free content, so they have hundreds of millions users around the world. We're just selling stuff, so you can imagine. But we do have a big table. The one I manage called reconstruction, basically it's provide the status of inventory for each individual client, so we can do a more deep analysis on that. And this table adding about 500 to 800 million rows per day. So, and it accumulates about more than 2 years of data. So in order to, let me introduce a little bit about our data infrastructure. We are kind of heavy Python and R, because majority of people in the team just came from academic like a background, are doing data science in various fields of science, and they normally use Python R on their local desktop. That's why we are a very heavy Python and R user. And a few people on the platform team, they use real engineering language called Scala, which is good news. Because everything is written, majority of data science jobs are written in Python R already, so we basically deploy them through a Docker container, like in production. So you probably heard about the Martin mentioning in the keynote this morning. There's a gap between the data science daily workflow and what's actually happening in the production, especially you're running job on Spark in production. Yes, there's a gap. It's not easy to fill. The way we do is we help data scientists like run a query as easy as possible, then like retrieve the result of that query as a Python pandas data frame or R data frame, so they can work on that part. So yeah, that's kind of the solution. I'm not sure that's very ideal. I mean, the migration from the all the Python flow and R flow, especially the API, to retrain all these data scientists to learn the data frame specific or Spark specific API is kind of like a not easy job. And also there are many tasks that really don't require big table. You can argue like a single machine with 1 terabyte in the memory, it can do tons of things. And probably a whole lot faster with a sizable Spark cluster if you're doing some machine learning in a Spark. So as business grows, of course, you can't always put all the data in the single machine. In the early days of Stitch Fix, we can do this. Now we cannot. So at that time, we start using Redshift to store all the data as a data warehouse, and basically it extract the data we need for certain tasks. Then we start doing all the data science job. So actually, there are a lot of advantages for Redshift, which is I think it's the first cloud-based data warehouse systems you pay by hour. You pay by the computation and the storage capacity you need, which is actually very cost-effective compared to any previous commercial data warehouse. It can be very fast with all the column storage and compression, and with properly designed disk key and sock key. And of course, you can design your index like all these things. It can be pretty fast. I remember the very first time I read about Redshift, written by some engineer from Pinterest. They say a query can be 100 times faster than in Hive, which is true. And also, it's talking very familiar interface in SQL that people already know. And it claims to be scaled up and down on demand, which is also good. The problem we have, probably kind of not, I'm not sure it's unique or like a general to other company, because we have so many data scientists that the trouble we have is like the Redshift has become like increasingly kind of become very, very slow in the morning because people start working in the morning. And so Redshift promised to scale up and down on demand, right? So that should solve the problem, but actually not. Actually, scalable doesn't mean it's easy to scale. The way Redshift scale up is by you can click up some button in the AWS console by adding more machine to the cluster, but at that point, it will stop writing. It will only, the cluster will become read-only. And internally, it basically repartition the data, reshuffling the data to the new nodes. So it basically, and this process can last a couple hours if you have tons of data, or even days, which is pretty bad. And even worse is when you finish this job, finish the query, you want to scale down to save some money, it will redo this job. They basically reshuffle all the data across the cluster. So another problem that we have as Stitch Fix is that we only have one Redshift cluster, although it's quite a big cluster. However, since when we finish doing these ad hoc stuff for development, we want to deploy in production. Then these production pipeline running the same query against the same Redshift cluster, so they share the same cluster, and that causes quite a bit of problem. Some people. You can imagine, especially in the morning, data scientists start writing exploratory queries. Some of the query may be buggy, or maybe very slow. It slow down a whole cluster, and all the production pipeline are just pending, and yeah, that's caused tons of trouble. So you may say, how about let's have another Redshift cluster only for dev? So let's keep one for production, another for dev. That should solve the problem. Not exactly. Now, first problem is you need to sync, since you have 2 copies of the data. Which one of them you trust the most? You have to make sure they are synchronized. And still, that doesn't solve the scalability problem. What if one class is full? How are you going to do with that? The fundamental problem, I think, in Redshift is there's no isolation between the computation and storage. I think this is not very obvious at the beginning, but gradually I see this problem. So that if you really want the computing power when you have lots of people using the system, or you have a very long query to finish as quick as possible, you can scale up. But you are paying the money for the CPU, but you don't really need the extra storage. And in another case, you have tons of data, and the Redshift the cluster is basically all the disks are kind of close to full. Actually, when the data inside Redshift is above 75%, I think that's like a rule of thumb. If above that level, Redshift will more likely to become kind of slow. So normally you want to add more capacity of disk to make sure all the data like below this certain level. But in that case, you are paying the money for the storage, not paying for more computation power. If, let's say, in the evening, nobody is using, or very few people query or production query running that, you still pay the money. It doesn't matter you use it or not. So as a solution, we decided to migrate from Redshift to Spark. So the very first thing we do is, just like I mentioned, because there's no isolation between computation and storage, we need to make sure these two things are separate. How are we going to make sure separate? So we clone and sync all the data to S3 as the first step. And during that phase, every table in Redshift will exactly have a clone in S3. And we use high meta store on top of that. So just to make sure it's compatible with all the existing Redshift table. So this gives us a foundation of the storage that later we can migrate to the Spark. Actually, the Spark cluster and the Redshift are running at the same time for quite a bit of time until we make sure everything's okay. Then we can shut down Redshift. So it's not easy. But now we treat S3 as a single source of truth. So that's we keep only copy, and kind of in practice, you can think of S3 as unlimited, like storage. So we don't have to worry too much about the storage limit anymore. So this is our current architecture of the Spark, like a whole environment for computation. It's probably not like a general, like other company, because we have a lot of people originally from Netflix. We are probably the only company using Netflix Genie in production. In a sense, like Genie is an open source project from Netflix, as you can think of it as a job server on top of a Spark cluster. The advantage is that it provides some abstraction to the client side. If we have many ways to run the job, we just submit to Genie, and Genie will submit to the Spark cluster. So we can dynamically change the configuration of Spark. Like say we have a new version. Let's spin up a new cluster on EMR with a newer version. Let's say Spark 2.1. Yes, you can do that, and while all the existing Spark cluster can running, or you have a certain job you want to backfill a certain pipeline, you need tons of computing power. Yeah, you can have an on-demand Spark cluster, and the client is transparent to the client. So the client doesn't need to know exactly know the IP address of that Spark cluster in order to use this. And actually, we are kind of running. Actually, when you deploy when you submit a Spark job to Genie, the driver node is actually running inside the Genie cluster, or the executor running in Spark. That's kind of the architecture we pick. So our main use case is Spark SQL. We're very heavy Spark SQL user, and with a little bit with the PySpark. Of course, because we already have all the query in Redshift, just very natural path with the lowest friction. The thing we do kind of special is we abstract away the storage layer. We don't directly use the default write these functions inside the Spark. The reason is like someone asked a question in the end of the previous talk, how we gonna address the eventual consistency problem in S3. The way we do, as also this is this project was invented in Netflix, is that every write is you create a new folder. You always appending data. You never overwrite. So with every appending, you basically internally use timestamp as a batch ID. So this batch ID only high meta store know which batch ID this current folder is pointing to. To the user, it always looks the same. It's completely transparent. So by doing that, we avoid the eventually consistent problem in S3. Although someone later commented to me like there's actually a more consistent version of S3. I haven't used that. Maybe there's some price there. I don't know. So there's some difference in Redshift and the Spark SQL. Majority of them are in function and the syntax. We have an internal document to help people migrate from one to other. There's just, I don't think it's that important that once you know how to convert, yeah, that's just the way it is. There's some syntax not supported in Spark. That's okay. I think the more important part is the conceptual level. On conceptual level, it's still due to, in Redshift, the storage and the computation are like the one thing. So when you talk about the partition in Redshift, which means the same thing, how the data like partition across different nodes in the cluster is basically the same way when they compute the way they partition when you run the query. However, in Spark it's different because Spark is just for computation. It don't care about how you store the data. You can store the data in this way, like for example, like a country, with a country as a partition, year as a partition, later months, whatever. But that's only kind of information you decide on the storage level, and that information stored in the high meta store. Then when we talk about, in the context of Spark, when we talk about partition, that is when Spark load data into the Spark cluster, then the way Spark decide how to partition the data across the whole cluster. So sometimes this can be confusing. The number of partition on the storage in S3 in this cases, when we normally you can think of it as number path file, may not be the same as the number of partition inside the Spark cluster. So there are actually ways to control this during runtime inside the Spark. You can either through Spark SQL. I don't think many people using this function. You can actually specify distribute by, or in the data frame API. In Redshift, you cannot change this during runtime or in your query. It only can be specified in your schema when you create the schema and load the data. And that's all. Otherwise, you need to recreate the table to change this partition key. This is the same for how you order the data. In Redshift, there's a sort key. In Spark, basically, you specify this. And this sort by actually is different from order by. If you look at the data frame API, it's called sort within partition, and this makes things a lot clearer. It's only sort inside each partition, and when you in SQL you say order by, it's order across all partition. So yeah, eventually when you go through this conversion on the syntax and function, it looks quite easy. You port the same kind of query from one system to another system. They all talk SQL, which is good. But as soon as you do that, you will find, oh, why is my query so slow? So there's a lot of performance issue we encounter. I think the key difference is Spark is an in-memory computation platform with SQL layer on top of that. And when we use Redshift, we never have to think about in-memory computation or not. You don't even know how Redshift is running the query in-memory or not. So this is the frequent asked question number 2 inside our Slack channel. Why is my Spark job so slow? And This is my favorite answer from my colleague Sonia. I got a query down from 2 hours to 4 minutes by simply catching the temp tables. Yeah, that's 30 times faster. Sometimes this simple trick can do amazing things, just catching all the temp table. And Spark, if the job you assign enough memory, it will try to catch as many temp table, as many data in the temp table as it can. Sometimes you will see in the Spark console, it doesn't have that much memory as resource. It only catch partial of that temp table. That's still fine. So other general rules, like I guess the speaker from the previous talk already covered many tricks. Use partition and filter. And big things to slow down your job is can be data not evenly distributed. This is still hard thing. Some of them data skewness, like inherited in the logic of your query. So you have to be careful. Another problem we encounter is it's called small file problem in S3. It's different from the problem like the speaker of a first talk like mentioned. Is that it's not about you reading a tons of file in S3. That's why it's so slow. It's because we have a folder. It's because other projects, when they write back to S3, they write too many small files, and the I/O cost for these small files is actually pretty high in S3 because the API call to retrieve the directory is far higher than to read the file itself. And so you may wonder, what's the frequent asked question number 1? Yeah, why my job failed? This is actually much harder to detect. Majority of them fail because of memory problem. And you can add more memory sometimes to solve problem. That's good luck. But sometimes it's probably hard. And still, data skewness is a big problem, like to cause many jobs to fail. We can repartition the data. Like I mentioned, the partition by. That may solve the problem. There's actually, because we are heavy using Spark SQL, there's actually a parameter that's kind of important in Spark. It's called shuffle partition. By default, it's 200. And this number is pretty bad, I would say, because in our case, our sum table was quite big, like a couple tens of billions of rows of table. That number is too small, because if you only partition data by 200 pieces, if any one of them exceed 2 gigs limit, and it would just crash. That's the limit of, I remember that's the limit of array inside the Spark or inside Scala. But for another extreme is if you have quite small data, sometimes my colleague asked me, I only read a very small table, only hundreds of lines. Why is it so slow to read this and do the processing? It's because it's such a small table, and 200 is too big. It causes a small file problem in S3. It creates too many tiny files, and the majority of the time are wasted down to retrieve the data, to retrieve the directory structure from S3. I want to briefly talk a little bit about the productivity. So I think, although the whole Spark community kind of very excited to using SQL, and SQL is very user-friendly to many people, like a very accessible language. I still think SQL as a language doesn't scale well. Now, in this case, I'm not talking about it doesn't scale across the machine or doesn't scale across data as you have lots of data. I'm talking about doesn't scale as you have more people in the team. Because I've never seen any SQL query longer than 100 lines that's easy to read in my experience. So any SQL query probably just like a JavaScript or PHP, sorry to blame these two languages, just you write it and you're ready to throw away and rewrite again at a certain point. So the structure of the SQL is highly nested. If you want to deal with complicated logic, you can subquery by subquery, a different layer of subquery. There's really not much tool to control the complexity of that in that language. The only one trick pony, as far as I know, is called a CTE, Common Table Extension. Oh, sorry, Common Table Expression. Basically, you extract these subquery into a with clause, with A, with B, and later you do something. So we have many very large, complicated queries follow this pattern. So if you translate this in Spark, you basically, for every subquery inside a with clause, you just create a new timetable for that. And if that query is really long, you can split them into multiple files. So just to avoid the problem that single file is too long. I think the better solution, we can draw some inspiration from other Dataflow kind of language. You probably already know that the Spark Data Frame API is a Dataflow kind of like a API. There's also PIX. That's like a couple of years. I'm not sure people still using it. Probably some big companies still use it. So you can chain the flow. You think about the data as a flow. You do all the transformation like a step-by-step as a pipe. This idea is pretty popular in other languages. In R, we have dpri, and also in Python, we have pandas pipe. Still, this idea is good, but the other function provided in these existing API are kind of like a low level. We still need some high level abstraction. The current kind of promising solution I've found is this DataSet API called Transform. It's not very kind of popular, or I haven't seen many people talk about this. It has been part of the DataSet API since 1.6, but 1.6 is like the DataSet API in 1.6 is very experimental. I guess people only start using DataSet since Spark 2. And in Spark 2, the dataset is kind of compatible with data frame, so you can call this to data frame as well. So you can imagine we want to know the lifetime value for all the active clients, across all clients. We can have a transformation function called with active clients. The input is a data frame, the output also a data frame. Inside that, you can implement all kinds of complicated logic. And another transformation function called with LTV stands for lifetime value. And with transform, you can basically chain these functions as a pipe. So you have the client transform to with active client. So as someone new to this file or new to this query, they can immediately figure out the purpose of this query. Because these are very high level. They hide all the complexity inside these transformation functions. So I think that's the way to go. Unfortunately, this is only available through the Scala API currently, not available through Python or R. So we're still trying to explore all the other possibility, or just to switch to Scala maybe in the end. So that's all. Thank you.
Questions? Thank you very much. Thank you also for the blog. My team likes your data science blog.
Thank you.
I got a question on how you got data from Redshift to S3. So did you use the unload command? And
yes.
If you did, how did you automatically found the tables schemas? And how did you convert to Parquet?
Yeah.
If you use Parquet?
So there's a internal script that unload the data from Redshift at the same time synchronize in the synchronize. Basically, we unload to a certain batch ID because we only store these internally in certain batch ID folder. So we have to update the high meta store to point to the new like a batch ID folder. So Spark or Presto they hit the high meta store, they will point to the new, like a partition, new folder inside S3. That's how it works.
And did you later convert the unload result to Parquet?
Yeah, that's a hard problem. We are still internally using compressed CSV as our file format. Parquet is on our like a long-term plan. The trouble is that historically we have a lot internal tools that allow Python and R to directly load data from S3 as a data frame. So we have to choose a file format that's compatible with all the systems, with Python and R. Especially with R, because R data frame, including the can contain categorical like data. It's not an array, it's like internal. Parquet doesn't support that kind of data well. We are looking for like the new Apache array project, array and feather, I think. That kind of like provide a seamless like a binary format between R and Python. And you probably remember Martin mentioned in the long-term plan for Spark in the morning, like that's also on the roadmap of Spark to support that in interchangeable binary format inside memory and outside memory. Yeah, it's a hard. We may plan to implement some file system, so we basically provide another layer of abstraction. So Python or R, they just call this API. I want CSV. This return CSV. Internal is Parquet, so that may be the temporary solution or solution in the near future.
One last question. With your team of 8 data scientists, how do you manage EMR clusters? Do each one of them fire up a cluster when they need, or are they shared clusters?
It's a mix. If you allow every job to fire its own EMR cluster, it's a long wait because you need to like a couple minutes, probably 10 minutes to wait until EMR cluster is available to you. So we have 2 constant running like a cluster, and they can scale up and down like on demand. Especially with recent auto scaling, like a new function introducing EMR like 2 months ago maybe. We are kind of probably gonna use that, so it will automatically scale up and down like on demand. So, and for a very big job, they can ask for on-demand cluster, just spin up a new cluster dedicated for some very heavy jobs. Yes, that's also, it's a mix.
Thank you.
Hi, thanks. That was a great presentation. Hey, I'm at Algebraic Data actually, and we're actually working on a product to like try to automate your fact number 1 and your fact number 2 problems, because we've seen a lot of the same problems, right? And we're trying to actually make a product to make it easier to get people off of Redshift onto Spark. And so I have to ask, what motivated you specifically to move to Spark instead of one of the other SQL on Hadoop solutions?
There are not many other alternatives. I mean, there's Impala or other, and also Presto. We actually use Presto, but Presto is so unstable. We only use it for ad hoc stuff. I mean, there's even not released version of Presto from Facebook. Facebook uses the master version all the time as well. So it has all kinds of problems. Like, but when it works very fast. But we don't recommend use Presto for production in a pipeline. Yeah.
That answers the question. Thanks.
No problem.
I think one more question over here.
Thank you for your talk. After you migrate the Redshift to Spark, to using Spark, have you shut down the Redshift?
We shrink the size of Redshift. Still there's some jobs. Still some jobs rely heavily on the Redshift specific like a function. For example, the age store, which is actually provided by like a Postgres kind of it's not directly supported in Spark.
And for cost perspective, after your migration, what's the change for the total cost?
Change for total cost?
Yes.
I think we don't really care. As an e-commerce company, we are pretty fat on the profit. Like we more concerned about the productivity cost. Actually, in the morning, everybody waiting, like doing nothing, and you think about 80 data scientists. You can think about their salary, and they do nothing in the morning. So, but that's a cost.
And what the tool you use to dynamically provision the new Spark cluster?
We use EMR, but there's some custom script to connect that to to configure that in the Genie. So the Genie know there's a new cluster. Then when people submit job to Genie, they can point to the new cluster.
Okay, thank you.
Yeah,
Okay,
thanks.
thank you very much, ladies and gentlemen. Please show your appreciation to Sky. Thank you.
Thank you.